How might these methods be useful in predicting the behavior of materials under different environmental conditions, such as temperature or pressure? What advantages does refining X-ray diffraction (XRD) spectra offer in terms of obtaining more information about the crystal structure and phase composition? How can refining XRD spectra help in determining the lattice parameters and structure of a crystal, and why is this important for material characterization? In what ways does refinement of XRD spectra assist in identifying phases and quantifying components within a material, and why is phase identification essential for understanding the material's properties? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does XRD refinement contribute to testing the lattice size, crystallinity, and residual stress of a material, and what does this tell us about its structural integrity and performance? How can the refinement process be used to determine the atomic radial distribution function, and what significance does this have in understanding the atomic arrangement within the material? What kind of information, such as bond length, bond angle, atomic occupancy, and occupancy rate, can be obtained through XRD refinement, and how does this contribute to a deeper understanding of the material's bonding characteristics? What are the three main refinement methods commonly used in XRD analysis, including Pauli, Liebel, and Rietveld, and how do these methods differ from one another? Why are these specific refinement techniques chosen, and how do they enhance the accuracy and reliability of XRD data interpretation? How can researchers choose the most appropriate refinement method based on the material being studied, and what factors influence this decision? How does the ability to refine XRD spectra impact the overall research and development process of new materials, particularly in fields like energy storage, catalysis, or nanotechnology? What role does XRD refinement play in improving the design and performance of materials, such as those used in sodium-ion batteries or other energy storage systems? What is the Pauli method in X-ray diffraction (XRD) analysis? And how does it calculate diffraction peaks based on lattice parameters? How does the Pauli method contribute to understanding the structural characteristics of materials, and why is it important for refining XRD data? In what way does the Liebel method differ from the Pauli method, and how does it calculate diffraction peaks from lattice parameters while also using lattice parameters and peak shape parameters as variables in least squares fitting? What role does least squares fitting play in the refinement process, and how does it improve the accuracy of XRD analysis? How is the Newton-Raphson mathematical principle applied in the Liebel method to minimize the difference between the calculated and measured diffraction patterns?